So a scalar quantity is a quantity that uses units without direction. There's no direction listed in the quantity. For example, volume. Volume, an example of volume would be like 10 milliliters. Milliliters is a unit of volume. And notice that I don't put a direction about the milliliters. I don't say, here's positive 10 milliliters or here's negative 10 milliliters. I just say 10 milliliters. So there's no direction listed. Same thing with temperature, okay? Unless we're talking about like -0 degrees, like when you go below zero, we don't have a direction when it comes to temperature, right? I don't say, oh, it's 30 degrees Fahrenheit east or 50 degrees Fahrenheit north. Temperature is just a straight number with a unit. Vector quantities are units with a direction, meaning they're an incomplete value if you don't give direction to them. For example, velocity. Velocity is how fast you're going. It's basically its speed with a direction added to it. So if I say, run after him, he went 50 miles per hour. That's not velocity because I didn't give you a direction. If I said, run after him, he went 50 miles per hour northwest. That now is velocity. So all of these units have to have a direction. You can use compass directions like north, south, east, west, or you can use directions like positive and negative. Okay. If I said, hey, he ran 5 meters in the positive direction, that means he went 5 meters away from the point of origin. And usually on a line graph, the positive direction is always going to be in the right direction, and the negative direction will always be in the left direction. So if I said he went -10 meters, I'm saying he went to the left from his origin. So we have to give direction with vector quantities, and really physics is all about vector quantities. Chemistry was using scalar quantities. You probably should see that a lot of these units here in the scalar quantities, those were chemistry related. But physics is all about movement, right? It's all about the study of movement. So we have to have direction in our quantities. Let's look at one of the vector quantities, which is displacement. And we're going to talk also simultaneously about this word distance, because distance and displacement, they not only sound the same, but they also almost mean the same thing. So distance is how far you have gone. Let's make that our definition. It's how far you've gone total from whenever you started. The displacement is how far you end up from the point of origin. Those sound almost the same. Let me give you an example so you can understand how they're different. Let's first show an example of distance. Our point of origin is 0. It will always be 0. Point of origin is wherever you start out before you actually start your movement. Okay, so here's our origin before any movement begins. Let's say I say you walked positive 6 meters, then you walked negative 10 meters, then you went positive 3 meters. Notice I'm giving you direction in all of these because distance and displacement are both vector quantities. I walked 6 meters in the positive direction. That means I walked all the way and I stopped right here. Then I walked 10 meters in the negative direction. So 10 meters in the negative direction would end right here, -4. And then I walked 3 more meters in the positive direction, so I end up right here. Okay, so distance is my total mileage that I've gone, that I've walked. First I walked 6 meters, then I walked 10 meters, then I walked 3 meters. When I'm adding up my total distance, I'm not going to keep any negatives because I want to figure out how much total distance I walked. If I included the negative over here, then that's going to end up not giving me the correct amount. So we can see from this basic math that he walked total distance of 19 meters, okay? His displacement, however, is not 19. Displacement is how far you ended up from the place where you started. Well, we know we started right here. This is our point of origin. We know we ended right here at -1. Just by visually looking, you can see your displacement was 1 meter, right? That's how far you ended up from the place where you started. His displacement was 1 meter. Displacement actually has a formula, though. You won't always be writing your problems on a number graph and a number line, and these numbers that I will be giving you in real life are not always this nice, neat, and clean. So using a formula can be very helpful. The formula for displacement looks like this. It's the change in distance. So it's your final distance minus your initial distance will give you your displacement. So my final distance in this case was -1. My original distance was 0. So it's -1 minus 0 gives me -1. Okay, that's my change in distance. That's my displacement. And displacement, we do leave our negative value. What this tells me, my displacement was -1 meters. That means wherever I started was 0, and I went a bunch of different places, but I ended up 1 meter to the left of my origin. Okay. If I had said your displacement was +1 meter, then you would have thought I ended up over here on the right side of the origin. So for displacement, you do need to include your negative values. This is really where we're going to camp out for the rest of the video on this formula. It's the formula for velocity. Okay, and velocity is the distance. It's very similar to speed. It's the distance that you traveled divided by the time it took you to travel that distance. We show average velocity with this line. That line stands for average. So whenever you see this line above the letter, that means average. And then the V stands for velocity. The delta stands for change in. Okay, both of these stand for change in. The X stands for position or distance. And the T stands for time. Okay. Let me break down this formula a little bit more. We know just from my previous example that delta X has its own formula, so I'm going to break that down into its composite parts. Delta X stands for the final position or distance minus the initial position or distance. And time can be broken down into a similar formula. The change in time is the final time subtracted by the initial time. Okay, so this is really the formula that I want you to get comfortable looking at and using. Velocity can be graphed on a y-axis, x-axis graph like this. You have to memorize what's going to go on the y-axis and what will go on the x-axis. In physics, time will always go on the x-axis all the time. This is the horizontal line. Time is on the horizontal line. And then your position or your distance is going to be plotted on the y-axis, okay? So if you notice, velocity, change in distance over change in time, looks a little bit like what you learned in algebra, that was rise over run. Rise over run stood for your change in y divided by your change in x. In our case, where do we find our change in x? And this x, by the way, is not the same as this x. This x is referring to the x-axis. This x, remember, is referring to position. Okay? So where do we find position graphed on our graph? Position, I just said, was in the y-axis. Okay? And what about change in time? Where do we find that? We find that right down here on the x-axis. So if you remember, What did rise over run or change in y over change in x give you in algebra? Anyone? Anyone? This is like Dora the Explorer. Do you guys have the answer? This right here was your formula for slope in algebra. So the formula for velocity looks a lot like the formula for slope, which is an interesting coincidence because whenever you graph velocity, the slope of the line on a position time graph, position time is called a position time graph because graphing position over time, okay? On the slope of the line on a position time graph equals your velocity. So we're going to do some problems with this. This slope of the line is your velocity. Let's go ahead and break this down and do some problems. Here is example 1. Let me get my child. He wants to do this example problem with us, and I told him he couldn't, but now he really wants to, so let's bring him in. Here he is. He wants to join. Do you want to join? Okay, he's very, very excited about this. Example 1. Bob ran 12 miles in 2 hours, which it's not awful. It's actually pretty good to run 12 miles in 2 hours. So to get a snow cone, obviously, because those are great, calculate and graph his velocity. Well, let's first just practice graphing it, okay? Remember what goes on our x-axis? It's time. And in this case, our unit for time looks like it's hours. So I always put my unit and my variable on the axis label. Always, always, always. On the right side here, we've got position. You can see I have a coffee date here soon. Position, and our unit for position or distance is miles. Okay, so position over time. And I'm going to go and graph that. Right now I'm only given 1 point. Okay, time is my x value, and then position over here was my y value. So I'm going to graph this point, 212. Let's say this is 1 hour and this is 2 hours. And then let's say we have 2, 4, 6, 8, 10, 12. Let's say that's 12 hours. So I'm going to graph this point right here. Okay. And the cool thing about a velocity graph is your first point is, well, actually it's not exactly true, but usually your first point is always 0. In this case, we're going to assume that your initial point is 0 unless I tell you otherwise, okay? So now let's connect these dots. This is his velocity graph. Now let's calculate his velocity. We graphed it, let's calculate it. Well, here's our formula for velocity. It's our final distance minus our initial distance divided by our final, whoopsies, our final time minus our initial time. In this problem, we see he ran 12 miles. So 12 miles is his final time, final distance. Always put your unit. His initial distance is not given to us. If it's not given to you, usually you can assume it's 0 miles. Okay, so I'm assuming it's 0 miles here. And then it's divided by, his final time was 2 hours. With time, again, you can almost always assume the initial time is 0. So 12 minus 0 is 12, and 2 minus 0 is 2. So here is his average velocity. Let's go and divide them, and I'm going to end up with 6 miles. And notice what happens with these units. When a top unit is divided by a bottom unit, you can put the slash, the diagonal slash, and then the other unit on the bottom. So miles per hour looks like this. And I do MI because in physics we use M to stand for meters. So if you have miles, go ahead and do MI/H. But that is the same thing as this, miles per hour. 2. This shows a race between Bob and Stefan. Okay, so let me use a different color, fuchsia. Okay, what is Stefan's velocity from 2 seconds to 8 seconds? So this is just like the problem we just did. So let's write out our formula. Velocity, average velocity, is our change in distance over our change in time. We know our change in time. We go from 2 seconds to 8 seconds. Well, which one's the initial? Where did you start? We started at 2, so this is our initial time. We finished at 8, so it's our final time. Remember, you always do final minus initial. Okay, so where do I get my distance values? Well, I can get those from looking right here on the graph. Stefan is right here, and this is Bob. So we're looking from 2 seconds, which is right here, to 8 seconds, which is right here. We need his final distance and his initial distance. Well, his initial distance is right here. Let's bring it over, and we're at 2. And I didn't give you a unit here. Let's say this is meters, okay? So 2 meters was his final, minus, this was his, I'm sorry, that's not his final. I lied, right? This is not his final, this is his initial. His initial velocity, right, if we're starting right here, this is an initial, this is his final. His initial position was 2 meters. His final was, looks to me like it's right at 8 meters. Okay, so here we are doing 8 meters was his final, 2 meters was his initial. It looks like we're having the same number on the top and the bottom here. This comes out to 6 meters and this comes out to 6 seconds. When I divide them, I get 1 meter per second. Okay, this next question is a variation of what we just did. I said, what's Stefan's velocity at 3 seconds? Okay, I've given you his final time, but I didn't give you his initial time. Do you remember what I said about if I don't give you your initial time, what are you supposed to guess? Or what are you supposed to assume? You're supposed to assume it's 0. So let's go ahead and do that. Here's our velocity. His initial time was 0. And his final time was 3. Remember, always list the final first. Sometimes I get them mixed up. So what's his final distance and initial distance? Well, he starts at 0, which is down here. That's his initial in this problem. And he stops at 3 seconds right here. So this is his new final. Okay, so what's his position here? Well, his final position is 3 meters. His initial position was 0 meters, which comes out to 3 over 3. And I forgot to put my units, so let me do that now. And I end up with 1 meter per second. You can see his speed has not changed, right? His speed is staying consistent here. From 0 to 3 seconds and 2 to 8 seconds, his speed is the same. The last question says, who's going faster, Stefan or Bob, and how do you know? Well, if you think about what this is graphing the slope, which stands for velocity. Okay, so the greater the slope, the greater the velocity. Which one has a greater slope? Stefan does. So Stefan is going faster than Bob because he has a steeper slope. Okay. Next problem, we're looking at a bunch of lines going in a bunch of different directions. There's 4 people, Andy, Barb, Stefan, and Bob. Okay. The first question says, what's Andy's velocity at 3 seconds? Okay, so Andy is right here. What's his velocity at 3 seconds? So we're looking right down here at 3 seconds. This is his final. Since it doesn't give us an initial, we're going to assume that the initial time is 0. So we're going to assume this is his initial. So what's his velocity? Well, it's the final time, which is 3 seconds, minus the initial time. And then it's the final distance, which is 3 meters. I'm assuming this is meters here. Minus his initial distance. What was his initial position? It's not 0, it's 10. This will be interesting. So 3 minus 10 is -7. 3 minus 0 is 3. So his distance here is -2.5 meters per second. Can you have a negative? Yes. What does a negative mean when we're talking about velocity? Means we're going backwards. He started at 10 meters away from the start, and now he's running to, oh, did I say he stopped at 3 meters? Oh goodness, I made a mistake. When did he stop? When was his final distance? It's 6. Silly me. 6. So this actually comes out to 4. So negative 4 over 3 is like 1.33. So his velocity is negative 1.3. But it's the same, I mean, what I was saying is still true. Whenever it's negative, they're running backwards on the course, okay? Explain everyone's position at 0 seconds. 0 seconds, what's happening? Well, Stefan is blue and Bob is blue. Stefan and Bob are at 0 meters, okay? Barb is right here. She's in the fuchsia color. Barb is at 4 meters. She got a 4-meter head start. And then Andy is already at the finish line. He's at 10 meters. Okay. At 4 seconds, what's happening? Let me change my color here. At 4 seconds, here's 4 seconds. So we're looking right here. What's happening to everyone at 4 seconds? Bob looks like he's right at 2 meters. So he went from 0 meters to 2 meters. So if I wanted to, I could calculate his velocity there. Stefan is right here. He's almost at 4. So Stefan is almost at 4 meters. I put minutes here. I meant meters. Notice what's happening to Barb. Barb started at 4 meters. What is she now? Barb is still at 4 meters. So she didn't move. So a conclusion we just made is a flat line on a position time graph means that there's no velocity. She has no change in distance, right? She stays at 4 meters the whole way. And then Andy was up here at 10 meters, and now he's right here, which is about 4.5 meters. So Andy ran backwards. So we could explain what's happening to all of them. We're not going to do the one at 5 seconds. And then we did talk about the difference between their slope. Stefan has a steep slope, so we could calculate his velocity, and we know he's going to have a high velocity. Barb's slope is flat. Okay, a flat slope means 0 velocity. Okay, this right here is just a summary of some of the things we discussed. Positive velocity means we're going forward. Negative velocity means we're going backward. 0 velocity means we're going nowhere. That's a flat line. Backward is a downward line. Forward is a positive line. Okay? A large value for velocity is translated by having a steep slope, like this or this. Okay, a steep slope. A small value for velocity is translated by having I said steep slope, steep slope. A less steep slope. So having something like this or this, they have lower velocities than ones with steep slopes. Now, these are 2 problems we're going to solve that are a little bit more complicated. You can actually rearrange your velocity formula, which looks like this, to solve for one of the variables. Instead of solving for velocity, we can use this formula to solve for final distance, initial distance, final time, or initial time. Whenever you're given a problem, the first thing you do is you label all your variables. That is super important. 1, label your variables. So I'm going to go through here and I'm going to label all my variables, okay? Stefan threw Bob's keys out the window and they landed. It took Bob 2 seconds to realize what Stefan did, and then 35 seconds to go grab the keys. Bob was standing 2.21 feet away from the window at the time. that Stefan threw the keys, and he ran to get the keys at an average speed of 6.5 seconds. How far did Stefan throw Bob's keys? So looking at this formula right here, I need to find all of these variables. It says that Bob ran to get the keys at an average speed of 6.5 feet per second. That's my velocity. I like to put a little check mark by my formula so that I know which variables I have. I have velocity. It's given to me. Okay, this is his velocity. It says that Bob was standing 2.21 feet away from the window at the time that Stefan threw the keys. So here's Stefan. He's our point of origin. Negative 2.21 feet away, this is Stefan, is Bob. And then Stefan threw the keys somewhere over here. We don't know. We don't know where it was. So what was Bob's initial distance? This is Bob's initial distance. We have his initial distance. Okay. We don't know his final distance from Stefan. So we don't know x of f. I'm going to circle that. Anything you don't know, go ahead and circle on your formula. Okay, now let's look at time. We need to find the final time and the initial time. Well, it says it took Bob 2 seconds to realize what Stefan did and then 35 seconds to go grab the keys. So let's draw another graph right here. Stefan threw the keys at 0 seconds. 2 seconds later, Bob realized, oh no, I need to go get them. Okay, 35 seconds later, which means this is now 37 seconds total, Bob grabbed the keys. So what was Bob's initial time? 0 seconds, right? So we have this, it's 0 seconds. What was his final time? 37 seconds. So we have everything in our formula except what? The only thing we don't have is final distance. So let's go ahead and plug in our numbers and rearrange. Our velocity was 6.6, no, not 6.6, it's 6.5 feet per second. Okay. I don't know my final distance, so I leave that there. My initial distance, we said, was negative 2.21 feet. Oh, look what we did here. If this was a negative, you got to leave it as a negative in your parentheses. Okay. Yes, I know you're ready for a nap. Now we do final time minus initial time. Our final time was 37 seconds. Our initial time was 0 seconds. Now I want to rearrange to solve for x of f. Well, how do I do that? First is get anything out from underneath the bottom of your, well, first thing we want to do is simplify. Okay, so let's change this to 6.5 feet per second equals the final distance plus 2.2 feet divided by 37 seconds. So I've simplified it. Now what I do is I'm going to get 37 seconds out from underneath the bottom. And the way you do that is by multiplying both sides. Anderson! Stop! Okay. Multiply both sides by 37. 37's gone. So let me rewrite it. This is us. 37 times 6.5 feet per second. This was 37 seconds. You got to keep those units. X of f plus 2.2 feet. How do I find x of f? Well, I'm going to move my 2.2 feet to the other side. Okay, now all I have to do is solve for my answer. I'm first going to do my multiplication over here, and notice when I take 37 seconds times 6.5 feet per second, my seconds cancel out. This is a second on the top, this second is on the bottom of the fraction. They cancel out. So my answer here is feet, okay? And let me get my calculator out. So we're going to have 37 feet times 6.5 So this is 240 feet. Okay, and then I'm adding it to negative 2.2, which comes out to 238 feet. So he ran 238 feet to get to his keys. And that is how you do a rearranging problem. And that's it for our video. Go ahead and do your practice problems for video number 1. And have a great day.